Okay, so welcome back. This afternoon we begin with a very interesting topic, really one of the very basic of computer networking, which is what we call the network reference model. The network reference model. For those ones that have never seen it, it might look a little bit technical, but I'll try to simplify it as much as possible. And if you go through it again and again, you should be able to get a better understanding of it. But I want to emphasize that this topic is very important. It's important that you understand how the network communication process is structured and broken down into layers, into a hierarchy. And data is passed from one layer to another layer as we either append or prepend information on it. So that is what this topic is about. So let's dive in. So in the digital era, various information is presented as data in our life. So what is data? What is data? And how is data transmitted? So in this course, we'll use the network reference model to understand the life of data. So by the end of this chapter, you should be able to. Sandra, please read out for us the objectives.
Understand the data definition and transmission process. Understand the concepts and advantages of the network reference model.
Yes.
Understand common standard protocols. Understand the data encapsulation and decapsulation processes.
Ah, wonderful. Thank you very much. Okay. So this particular chapter has 3 subtopics: applications and data, then the network reference model and the standard protocols. Then also we're going to now summarize this whole thing into what we call the data communication process, now to understand the whole bit of it. So let's begin. So maybe you can begin by, first of all, the definition of data. What is data? What is data? What is information? Yes. Yes, Anthony.
Data is unstructured facts, raw facts.
I like that one. Very accurate, very accurate. So you are saying, annotate, data, raw facts, and information.
Information is the data that
Wonderful. Thank you very much, Anthony. So data is raw facts, information is processed data. So generally these facts, before you've been able to, before you process them in a computer so that they can make more sense, then they're called data. After you've processed them and now they're easier to read and interpret, then they're what you call information. So generally, we have what you call data generators. Data generators, and generally, most of the time, we have applications in your computer that are generating data. So applications are used to meet various requirements of people. So they perform specific tasks. They enable you to perform specific tasks. For example, web pages will help you to, a browser will help you to access web pages. You might have an online gaming application or an online video playback like Netflix, for example. So those are applications, and they might generate information. So information is generated along with applications. Information ranges from texts, pictures, videos. So all this can be a virtual reality image. So I hope we get the difference between applications and information. So these applications are used to generate data. So data generation and data transmission. So in the computer, data is the carrier of all kinds of information. The carrier of all kinds of information. On the other hand, data that is generated by these applications, most of the time, they need to be transmitted between devices. They need to be transmitted between devices. As we all understand so far, computers communicate via a language called the binary language, right? The language of zeros and ones. So binary language, zeros and ones. So a computer is an electronic device that is made up of integrated circuits. These integrated circuits are what make up the processor. So the processor will keep on switching these circuits on and off to shift between 0 and 1. And therefore, whenever we give the computer data, then this data has to be converted from whatever we are typing. For example, when you type an A, it has to be converted into zeros and ones. And we have various representations that are used by computers to do that. Okay. So whenever we need to transmit data between devices, then that is where the network comes in. That is where the network comes in. Are we together? Huh? Yes. So that's why the network is important. One of the main functionalities of computer networks is sharing of information. Otherwise, other uses of the computer network, for example, is to share devices, to share load. You can share a device over a network like a printer. You have an office with 30 employees, but they're all printing from the same printer. So you're sharing a device. You can share load. You can have a powerful server that can be used by several people at the same time.
Hello, teacher.
Yes, please.
Is it also correct to say that besides sharing of information, computers are also used to generate the information or data?
Yes. It's very correct. So the computer is also used to generate information, to store information, and of course to also transmit information. So that is very right, sir. Okay, so now let's go into what we call the network reference model. Here we are going to look at a number of protocols that are used to do this. Now, generally, the reference model that we're going to look at is, number one, what we call the OSI, layered model. And the second one is called TCP/IP. TCP/IP, it's also a layered model. So OSI stands for Open System Interconnect. Is it interconnect? interconnect, right? And normally it's called a reference model. A reference model. So really, it's called a reference model because it provides a hierarchical model that is used to show how data is being processed. To break, it actually breaks up the huge communication process into specific tasks that are being performed at each particular layer. Are you getting the point? So really, the reference model helps to simplify the understanding of the communication process. It also helps to place different protocols at different layers so that we can be able to understand their functionalities and place them at particular parts. So normally, the OSI layered model has 7 layers. It's made up of 7 layers, while the TCP/IP layered model is made up of 5 layers, as you're going to see. Are we together? Now, these layers, they are numbered. The OSI layers are numbered from top to bottom. You remember when we were saying that a switch is a layer 2 device? It simply means that the switch belongs to the data link layer. When we say that a router is a layer 3 device, it simply means it belongs to the network layer. So layer 1 is called the physical layer, then the data link layer, then the network layer, layer 4 transport, layer 5 session, layer 6 presentation, and lastly layer 7, which is the application layer. So that's how they are numbered. Now, even before I tell you the function of each of the layers, you can use this. I don't know. Is it called? You can use this. All primary school teachers need daily practice. So you can use this to remember the 7 layers of the OSI layered model. Are we together? All primary school teachers need daily practice. So A for application, P presentation, S for session, T for transport, N for network, D for data link layer, and P for physical layer. What do we call this kind of song that is used to remember something? It's called a not acronym. Acronym ni kama OSI.
Mnemonic.
Mnemonic. I think it's something like that. Thank you, Sandra. Mnemonic. So you can use this mnemonic to remember the 7 layers of the OSI layered model. Okay, so normally when we are sending data, the data moves from the application layer all the way to the physical layer. So that's when we are sending. Otherwise, when we receive on the other end, the data will move from the physical layer all the way to the application layer. So just broadly, I just want to mention broadly the functionality of these layers because we are still going to look at them individually. So in summary, the application layer is used to provide interfaces for applications. Really, the application layer provides protocols that enable applications to access the network. Let me repeat that again. The application layer will provide protocols that will enable your computer applications to access the network. Are we together? Did I define what a protocol is? Because we're going to be looking at, so did I? Huh? Protocol. A protocol is a communication. A protocol rules that guide communication. Rules that guide communication in a computer network. Someone has mentioned this standard. Sometimes they also call standards, standards, protocols. So that is what a protocol is, provide rules. So at each of these layers, we are simply going to learn a number of protocols that enable data to be processed at that particular layer. Are we together? So at the application layer, when you talk about the application layer, we're talking about protocols that enable your computer applications to be able to access the network or the internet, or to process data in a way that it can be forwarded on the internet. So for example, one of the applications that you regularly use to access the internet is your browser. Are we together? Now when you're using your browser, when you type facebook.com, it will automatically insert HTTP or HTTPS. We used to type it before, but nowadays it automatically inserts for you. Because HTTP, which is Hypertext Transfer Protocol, is the protocol that enables the transfer of web pages over the network or internet. Is that clear? So that is one of the protocols that operates on the application layer. We are going to also see another protocol called FTP, File Transfer Protocol, that enables you to download files. When you're torrenting, downloading files from servers, you're using File Transfer Protocol. So it's an application layer protocol. So on each of these layers, make sure you understand a number of protocols that enable data or information processing on that particular layer. Okay, so after that, the next layer here is the presentation layer. Now, presentation, you can think of it as formatting. Are you getting the point? Formatting data in a way that it can be transmitted. In a way that it can be transmitted. Just formatting the data. In a way that it can be transmitted over the network. So at the presentation layer, we have things such as data encoding. We have different encoding mechanisms. I'll want you to research on that, data encoding mechanisms. So we have different data encoding mechanisms. We don't teach that here, but if you're doing IT, most likely you've met that. And also conversion of data. Conversion of data from, so data translation. So translate data formats. It translates data formats to ensure that application layer data of one system can be identified by application layer of another system. So data encoding, conversion, from maybe ASCII to, have you ever heard of ASCII? The American International Standard for something, information interchange. So those are the kind of things that happen at the presentation layer. Then after presentation layer, we have, of course, the session layer. As the name suggests, this one is used to establish, manage, and also terminate sessions between the communicating parties. Are we together? So to establish, to manage, and terminate sessions between communicating parties. So that is what happens on the session layer. Then you have the transport layer. Normally, we say that the transport layer does end-to-end data transmission. End-to-end data transmission. It also does what we call flow control. It does flow control. Flow control is simply controlling the transmission speeds. Are we together? Yeah? Yes. So for example, Facebook servers can be able to transmit at 100 gigabits per second. But your smartphone, which you're using to access the Facebook server, can only process 10 megabits per second. So your phone has to tell the server, hey, if you're sending data to me, I only have the capacity of processing 10 megabits per second. So send with this speed. So that is what we call flow control. Flow control. Then it's also used to adjust data sequences. Really, at the transport layer, you are able to sequence data because data are sent in chunks. So to number them, and you're going to see just now because you're going to learn about it. You're also able to detect in case you lose any data segments. So generally, we've said that at the transport layer, we do end-to-end data transmission, flow control, and also error checking and retransmission in case you lose data. Then the network layer. The network layer is used for logical addressing. Remember, we said we have a logical address and a physical address. So when the data reaches the network layer, that is where the IP address, source IP address and destination IP address is inserted. Are we together? Yeah, and of course, now it is also used to determine the path by which the data is going to be sent. The router is going to do that. Then at the data link layer, we have the physical addressing. We have the physical what? Addressing. It encapsulates packets into frames. So we have that. We have physical addressing at the data link layer. It transmits frames in P2P, point-to-point, or point-to-multi-point mode. It also implements error checking. So we can also be able to implement error checking at the data link layer. So we're going to look into that. Then at the physical layer, this is where we now convert the data from zeros and ones into either electrical signals or light signals or radio waves if we are using wireless medium. Are you getting the point? So it's at the physical layer that we implement the conversion of data into a particular format that can be transmitted using a particular medium. Is that clear? Is that clear? Yes. Okay. So don't worry, it might sound like a lot right now, but you're going to understand it with time. Now, the TCP/IP reference model is not very different. It is not very different from the OSI model. As you can see here, the TCP/IP model simply combines the first 3 layers of the OSI model into a single layer called the application layer. It also combines the last 2 layers of the OSI model into a single layer called the network access layer. Otherwise, transport layer remains transport layer. It's not even host to host or something. Network layer remains network layer, but you might also call it what? Internet layer. The functionalities of the layers remain the same. Okay. Now, let's look at a few protocols here. As I said earlier, you should view each layer. So right now, from here going forward, we're going to be looking at really these protocols using the TCP/IP layered model rather than using the OSI layered model. Are we together? Yeah. So we have several application layer protocols. I had talked about the hyper transfer protocol, HTTP. So HTTP is used to enable the transfer of web pages over the network or internet. So it enables you to access web servers. Is that clear? Yeah, websites really. So whenever you're accessing facebook.com, you're using HTTP. Are we together? Okay. Then we have FTP. FTP is file transfer protocol. FTP. So FTP is used to provide a method for transferring files. So you're able to transfer files from one host to another. So we can set up a point-to-point connection between my laptop and your laptop, and we transfer files. So we're going to be using FTP for that. Then we have, we're just mentioning a few at each layer. Here we're also looking at DNS, domain name service, DNS. DNS is used to map domain names to IP addresses. So facebook.com is what we call the domain name. Now, when you type facebook.com, that packet is not going to go with a destination address of facebook.com. No. It must go with a public IP address. So on the internet, that packet is going to go with a public address, public IP address, and not facebook.com. So normally we have a server called a domain name service that maps that facebook.com is at 200.10.10.3. Are you together? So when you type facebook.com, it gives your computer the IP address of facebook.com. So that is what we call a DNS. So those are just a few of the application layer protocols. Then at the transport layer, we have TCP. We have two main, TCP and UDP. So this one is transmission. Sorry, control protocol. So I won't talk much about this because we're going to learn about them just now. Then we have UDP, which is user datagram protocol. One of the main differences between TCP and UDP is that with TCP, it provides connection-oriented communication services. Connection-oriented means you have to form a connection before you start exchanging data. On the other hand, with UDP, it is connectionless communication. Connectionless means you just start sending data. You just start sending data without establishing a connection first. Are you getting the point? Yeah, so TCP is connection oriented. UDP is connectionless oriented communication. The other difference is that the other main difference between TCP and UDP is that we say that TCP is reliable, while UDP is unreliable. TCP is reliable because when a data segment is lost, it's going to be retransmitted. How do we recognize that we've lost a particular data segment? Because when you're transmitting using TCP, every segment we send has to be acknowledged. So I send you a segment, you say, I name it 1. Then you say, hey, I've received 1. I send you 2, you say, hey, I've received 2. Are you getting the point? But with UDP, we don't have that. We don't have acknowledgements, and if we lose data, we don't resend. Is that clear? Yeah. So that is the other thing about UDP. Okay. So we are going to learn further about this, but let's move on to the network layer. So at the network layer, we also have the IP, the Internet Protocol. Internet Protocol. We also have IGMP, the Internet Group Management Protocol. And we also have ICMP, the Internet Control Message Protocol. So of course, it's good that you know at least a few protocols in each of the layers, because it's a question that can come in the exam. In the exam, you'll have true or false questions. So for example, you can be told that ICMP operates at the application layer of the TCP/IP protocol suite. So you'll have to choose between true and false. What will be the answer to that question? Huh? ICMP operates at which layer? The network layer. So the Internet Protocol, it encapsulates transport layer data into data packets, meaning it simply adds the destination and the source IP address so that it can be transmitted over the network. So that is what the IP does. IGMP, Internet Group Management Protocol. IGMP, there's a very comprehensive video I made for this one, for the HCIP training. There's what we call a multicast. We talked of broadcast, unicast, and multicast. Do you remember? So with multicast, sometimes a server wants to send data just to particular computers that have joined a particular group. So, for example, if you want to watch DSTV over the internet, the DSTV servers have to send not to everyone on the internet, but just to those ones who've maybe logged in and are currently watching. Are you getting the point? Yeah. So multicast, we said, is one to a group. You send one message for a particular people that are in a particular group. Are we together? Yeah, that is what we call multicast. Now, IGMP is used to set up and maintain membership between the host and their multicast source. Between the host and the multicast source. Are we together? So that is what we call IGMP. So when you're joining the group, whatever maintains that and knows who is in which group is IGMP. But you can learn more about multicast from my YouTube channel. It's a very, very interesting topic and one of the main applications of networks today. Okay, then we have Internet Control Message Protocol. It's called ICMP. ICMP, on the other hand, is used to provide information about any problem that might arise. During the communication process. You can also use ICMP to troubleshoot your network. Have you ever used ping? Have you ever used the ping application? Ping. Ping is used to test the connection between your computer and another computer. For example, if you wanted to test whether, most of the time, if you want to confirm if I'm connected to the internet, I ping the Google DNS servers at 8.8.8.8. Simply write, I go to command prompt, I write ping 8.8.8.8. Then if I get replies from that server, I know that I'm connected to the internet. So if I'm not able to access the internet on my browser, then maybe there's a problem with the settings on my browser. Maybe I had set up a proxy server or something. But ICMP simply used to troubleshoot, diagnose your network, and to also report on any problems that might be occurring on your network. So I hope we learn about that when we learn about network operation and maintenance. Okay, then at the data link layer, we have the point-to-point protocol, PPP. Sorry. We have PPP, we have Ethernet, and we have PPOE. Now, Ethernet is used in our LANs. Are we together? In our local area network, the protocol that is used in our local area networks to send data at the data link layer is called Ethernet. It's the most widely used. Otherwise, PPP and PPOE are used for WAN connections. You know what WAN is? For wide area network connections. So we're also going to learn about these protocols. We're going to learn about them much later. Okay, so this is what I was mentioning when we were talking about open standards. So these are some of the very important protocol standardization organizations. I'm very happy that in Datacom they included this because I think it's very important information. So we have IETF, the Internet Engineering Task Force. The Internet Engineering Task Force. IETF voluntary organization responsible for developing and promoting internet protocols, especially TCP/IP protocols, SUT, and releasing new or replacing old protocol standards through RFCs. So RFCs is something we call request for comments. Request for comments. Please, 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 as young network engineers, especially from the African origin, please join IETF and contribute. Learn with others and contribute to the development of the internet, especially the technical bit of it. We have, the reason as why I'm making that call is because I'm aware that we have very few Africans volunteering in these protocol standardization organizations compared to other nationalities. So please join IETF. I'm very happy because one of our engineers here has made quite some contribution in IETF, and it's actually a lady, and they were working on the new called NetConf. He was in this special interest group. They're working on this protocol that should replace which there's another protocol. And network simple network management protocol, SNMP. So they are working on this NetConf, which should replace SNMP. And SNMP is simple network management protocol that enables you to be able to configure your networks remotely and also receive alerts if you're having problems in your network. So please, it's free to subscribe to their mailing list so that you start learning. The good thing is that once you're active, once in a while, if the pandemic is over, they can always pay for you fully paid trips to go for their conferences. Normally they have conferences yearly where they bring together people who've been working on several things so that they can be able to conclude them. So IETF, Internet Engineering Task Force, we also have IEEE. We talked of IEEE, right? Look here, it has formulated about 30% of the standards in electronics, electrical, and computer science fields worldwide. So one of the well-known standards is 803. 803 is for Ethernet. Then 802 is what we looked at earlier. 802.2 is for Wi-Fi. .3 is Ethernet. Ethernet is the communication in the local area network using cables. Then, have we heard of ISO? ISO international organization that plays an important role in the formulation of computer standards. So one of the ISO standard is actually the OSI model. The OSI model is an ISO standard, International Organization for Standardization, developed the OSI model. So you can join this protocol standardizations organization in order to contribute to the development of internet. Locally, you can also join Internet Society. They have very good trainings and tutorials that are free, like trainings to do with, for example, community network. So Internet Society really deals with mostly policy issues about the internet and also some technical bits. In Africa, we also have AFNOG, we have Afrinic that deals with the numbering. We are going to look at Afrinic later, which are, so you can Google about these ones. In Kenya, you can also join the Kenya ICT Action Network, also deals with policy. Kictanet. You've seen in job advertisements, they add a tag that belonging to a professional organization is an added advantage. It can be a tiebreaker if all of you have the same qualification, you performed the same in your interview. This can be a tiebreaker. Are you together? Yeah, so just subscribe. Subscribe to one of them, start learning how they operate, and within no time, you can start contributing. So they're very important. They're very important. Please, please, please. So let's begin now looking at each and every layer in detail. So the first layer we're looking at is the application layer. So as we said, it provides the interfaces for application software. So that is what we said. So that these applications can be able to use the network services. So the application layer protocol designates transport layer protocols and ports. PDUs transmitted at the network layer are called network layer. This is wrong. It's supposed to be application layer. Are you together? The PDU at the application layer is called data. Now let me start by telling you what a PDU is. Protocol data unit. So a PDU is a protocol data unit. Protocol data unit. So as data is passing from one layer to another layer, we call it a PDU. Are we together? Are we together? Now, this PDU at different layers will contain different information, because at each layer we are going to add some header or some footer, and therefore at each layer the PDU will go by different names. Are you together? Huh? So the PDU, as you've heard here, will be called data. When it comes to the transport layer, it will either be called a segment if we are using TCP, or we can call it a datagram if we are using UDP. Are we together?
What is the full form of PDU? Sorry?
Protocol data unit.
Thank you.
Protocol data unit. Okay. And then at the network layer, you must have heard of this one. The PDU is called a what? At the data link layer. Huh? Exactly. At the data link layer is called a frame, and at the physical layer, huh? Zeros and ones. Bit stream. It can be electrical signals, light signal, bit stream. It's called bit stream. Okay, so let's go back to the application layer. Some of the protocols. So it's important that when you know the protocol, you also know the transport layer port number and protocol that is used. Are we together? So we've already talked about HTTP. It's just important that you know that the TCP port number that is reserved for HTTP is port 80. Are you together? I'm not sure whether you understand what a port is, but generally it's just a logical listening space that is reserved for a particular application. So when you talk about port 80, port 23, we're just saying that we are listening at a certain logical port number. We come and listening through a particular ear. Listening through a particular ear for TCP. So anytime we have a request, we check, is it HTTP? If the destination is port 80, is it HTTP? Like that. Then we have telnet. Telnet port 23. Telnet is used for remote access, remote management services, remote access, remote login. It's a remote login protocol, meaning that you are in Angola, but you are able to access a server, your server in DRC Congo, remote login. So another protocol that operates at the application layer is FTP. FTP uses two ports, port 20 and port 21, file transfer protocol. It also uses TCP. So don't worry, we're going to tell you what 20 and 21 are used for. We're going to learn about that. Then we have SMTP, simple mail transfer protocol. This one is used to transfer emails, simply called mails. Simple mail transfer protocol. Internet email services, provides internet services. It also uses TCP. Then we have FTP and we have TFTP. We have TFTP. TFTP is trivial file transfer protocol. Unlike FTP, it uses UDP. It uses UDP. So it simply means that when you're sending using TFTP, you don't need to form up a connection and you don't need to do retransmissions. So it will be a little bit faster, but not very reliable. So simple file transfer protocol, which provides simple file transfer services. So each one has its own advantages and disadvantages, which I'm sure we're going to look at later. Kumbe, it's not even later, it's now. Anyway, so anyone with a question, by the way, or comment? Comment, question, anyone? Okay, so let's just faster go through this because I think we've already said more than enough. So FTP in full file transfer protocol. It will transfer files from one host to another in order to implement either download or upload of files. Are we together? Normally, it adopts what we call a client-server structure. A client-server structure. So what does a client-server structure mean? It means that one person will act as the client while the other person will act as the server. So the client can be able to download files from the server, and the client can also be able to upload files to the server. Is that clear? Okay, so of course, you're going to see much later that that actually routers, for example, can work as either FTP clients or FTP servers. So you're going to see that. And that's why it's important that you understand these protocols. Okay, so let's move on and look at Telnet. Telnet is a standard protocol that provides remote logging services on a network. Remote logging. So it provides users with the ability to operate remote devices through local PCs. So that is what Telnet does. So how does it happen? Again, it also takes the client server approach. So we have a Telnet client and a Telnet server that are connected over a network. So a user connects to a Telnet server through the Telnet client program. The commands entered on the Telnet client are executed on the server, as if the commands were entered on the console of the server. As if the commands were entered on the console of the server. What that means is you're going to see that when, for example, we configure our router, we are going to be configuring that through a textual character user interface. So that's what we're calling a console. So when you telnet into a device, it simply means that as a network administrator, you don't have to go and connect directly to that router to configure it. You can be sitting here in your office, and because you're on the same network, you use an application like for Windows, we normally use an application called PuTTY. Have you heard of PuTTY? To telnet. So if you open PuTTY, you can be able to log in into a router that is in the admin or a switch and be able to configure it as if you've directly connected to that router using a console cable. Richard, as if you've connected directly using a console cable. So you're going to see that for the very first time configuration, when you want to configure for the first time a router or a switch, you normally use a cable called a console cable. So with PuTTY, it can help you to telnet. It can enable you to telnet. So that is what we call telnet. Remote login and access. Yes. Even that one, because generally printers use serial cables, and a console cable is also a serial cable. But this one is a specific name for that kind of cable, console cable. Okay. Let's look at. Let's now look at HTTP. Hypertext Transfer Protocol, we've already talked of this. It was originally designed to provide a method for publishing and receiving HTML pages. So normally on your computer, so HTTP also adapts a client-server model. We have a HTTP server and client. So when you type Huawei.com, then your request is going to be sent over the network or internet. If the server is found, it's going to look at the resource that you've requested for, and it's going to return it to you. Then you're going to see it on your browser. So that is what we call HTTP, and that is how it is used. So now let's look at a few transport layer protocols. Transport layer protocols receive data from an application layer protocol, right? It receives data from what? Application layer protocols. Then it can encapsulate the data with the corresponding transport layer header. So it adds a header. Then it helps to establish an end-to-end, what we are calling a port-to-port connection. So the PDUs transmitted at this layer are called, they're called what? They're called segments. So at the transport layer, we say that we can either use TCP or what? UDP. One of them is connection oriented, the other one is connectionless. Are you seeing that these protocols have been developed by IETF? The Internet Engineering Task Force. Wonderful. So nothing more to say about that. Just as a summary, and end to end connection, flow control, and error detection and control. So those are some of the functions. Error detection, if we've lost a segment, we're able to retransmit it. Flow control, to control the speed of communication, okay? End-to-end connection through the port numbers. So that is what the transport layer does. Oh, so here we're going into this. So I think this is the very first protocols that we are looking into in terms of looking at the fields. So I just wanted to let you know that every protocol that you're going to look at, or every protocol, has what we call fields. They're called fields. A field is used to store some information. Used to store some information. Now, each protocol will have several fields. Now, for example, here, let's separate these two. Above here, we have the TCP header. So all the fields of a protocol define all the components that particular protocol has. And for example, for TCP and UDP, they are simply headers. So the header that is going to be added, the information that is going to be added to the data payload by TCP are this. So these fields are going to be added. One of them is the source port. So the source port is a port number. Are we together? The source port is a port number. This port number is randomly generated. It is randomly generated. It has to be above 1023. So it can be 1024, 1025, and so on and so forth. It's randomly generated. Are we together? Then we have the destination port. Now, the destination port has to be a specific port that we want to go to. Are we together? For example, we said HTTP uses port 80. You remember? Uses port 80. So any web server will be listening on port 80. So if we want to access a web server, we have to send a request, and the destination port number on the TCP header is going to be 80. Are you getting the point? Yeah? Yeah. If it's FTP, maybe 20 or 21. If it's Telnet, is it 23? So you have to know those. You have to know the port numbers for each of those protocols. Are we together? Not all today, but of course now you have to revise, and you should expect those questions in the exam. The other field on the TCP header is the sequence number. So every data that is sent over a TCP connection has a sequence number, is defined by a sequence number. So this sequence number field really will be the one that will store that sequence number, and we're going to see that just now. Then we have the acknowledgement number. As we've said, with TCP, if we send a segment, you have to confirm that you've received it, okay? So when you're confirming that you've received it, you give us that number of what you've received in this field. Are we together? Yeah, so that is what happened. Then we have the header length. The header length really means the length of the TCP header. The size. By length, we mean the size. Are we together? Eh? Yes. Is it 10 bytes? Is it 20 bytes? What is the size of this header? All this information that we've added, what is the size? So that is the header length. Then we have reserved. Anytime we have a reserved field in any protocol that we're going to look at, just know that it means it's not being used. Are we together? Huh? Reserved means we are reserving it for future functionality. So this one will just contain a value of 0. So we are not using it. Okay. Then we have control bits. This one is important, control bits. We have 3 control bits. Control bits can be fin, arc, or scene. We have those 3, or scene flags. So fin simply means, as you might have already guessed, finished, acknowledge. This one is for really sequence numbers or something like that. So we are going to see what each one of them means. So when the control bit arc is set, it simply means that we are acknowledging receipt of a certain segment. When fin is set, fin, it means we want to terminate this TCP connection. So we set the fin flag. Finished, we've finished, we want to, so we're going to see just now. And then scene is if we're just communicating normally and exchanging data. Then we have a window. You remember we said that one of the tasks of the transport layer is flow control, right? And flow control is ensuring that we only receive the amount of data that we can be able to process at a particular time. So it is on the window field that we tell the server at Facebook, hey, please, I can only process 10 megabits per second. So don't send me at 100 megabits per second, because I'll drop those packets. Can't be able to process. It's like you trying to process someone who's talking at the speed of a rapper. So you can't understand them unless they slow down. So it is on the window field that we tell them, hey, you can be able to send only this size at a go. Checksum, you're going to meet this field in many other protocols. Normally, this is used as a security field to confirm the validity of that particular segment. So normally it is calculated and stored by the sender. Then it's going to be verified by the receiver so that it can be able to find out if this segment is legit, coming from a legitimate source and not a fake. So that is checksum. Agent, as the name suggests, is used to mark if a particular segment is urgent. So the priority, just like on the roads, there are certain vehicles that have higher priorities, like the ambulance. So on the network, sometimes we have packets that have higher priorities. So the urgent field can be able to implement that. It indicates that the sender transmits data in emergency mode, and therefore it needs a higher priority. Options is optional. and normally it might have extra information or nothing at all. Are we together? Then of course, what is this? The data that we've received from the transport, from the application layer. Are we together? The data that we've received from the application layer. Now, one other advantage. Now let's look at UDP. This is the UDP header. One other advantage of UDP, in fact, I think it's the only advantage. Okay, let me just say one of the advantages of UDP over TCP is that the UDP header is very small, just 8 bytes compared to how many bytes for TCP? 20 bytes. So meaning a UDP header can be able to carry more what? More data payload. Are we together? Does that make sense? Yeah. Does that make sense? Yes. Yeah. So because UDP does not have so much it doesn't have so much processes, it only has these four fields: source and destination. Then it also has the length. We already know what these fields do, and the checksum. That's that. So we've already described those 4 fields with TCP. So is that okay? Yes. Anyone with a question or comment?
Yes, I have a question, teacher.
Please go ahead.
On the agent part, where an agent packet is actually sent over an application. What actually formulas are used to ensure that a packet is actually urgent? Or how do we do that as an engineers? How are we supposed to do that if we want our packets to be urgent over the network?
Okay. There's what we call traffic engineering and policing. So there's a way you configure traffic in your network to prioritize traffic from certain segments of your network so that you give them more priority, more bandwidth. For example, when you're setting up your network, sometimes you might need to give the managers a higher priority, higher bandwidth, so that they can have higher speeds for your network. And maybe, for example, in a campus environment, maybe not the same speed as the lecturers and maybe students. So again, that is one of the very topics that we teach in HCIP. You can find time and look at that topic on my YouTube channel on traffic engineering and traffic policy to understand how to implement that.
Thank you so much, teacher. You know, I've been using some of these things, but I didn't know actually. Like you just talked about it. On my side, we call it bandwidth shaping.
Okay. Thank you, Maurice. Okay, so I don't know. Are we moving so slowly? What do you feel? How is the speed?
The speed is good from my side, that is. I don't know.
Okay, Alain and Dennis, how is the speed? How is the speed so far? Okay, so I'm not too fast, I'm not too slow. Yeah. I'm feeling like I'm really slow today, I don't know why. Okay, let's move on. It's, yes.
Yeah, I'm wondering if you still take the chance to be practical today.
Why can't we just continue? Then we see if we can get there. Okay? Yeah. If we don't get time to do the practicals today, maybe I can record on Monday, then I can upload so that you watch and do it at your own time, okay? Yeah, but I really don't encourage this. I'm just wondering. Sometimes I like starting very slow, especially with the basics, so that everyone can move along and also create interest. But next week I'll try and I'll be a little bit faster. Okay, so it's important that you understand the concept of TCP and UDP port numbers. They're very important. Now, as we've already seen on the TCP and UDP headers, you'll have, sorry, I think I'm highlighting the wrong thing. I'm just trying to, okay, sorry. I'm trying to understand something here so that I can explain this. Okay. Destination IP source port. Oh, that is what I was looking for. I was looking for the TCP header. I'm sorry, and I wasn't finding it. Okay, so you see, we have a source port number. We've already said that. We've already seen that on the TCP and UDP headers, we have the source port and destination port. Okay, are we together? Now, it is important to know that the client will randomly generate a source port number. Are we together? Randomly generate a source port number. Now, that source port number that you randomly generate, it has to be two conditions. It has to be above 1023, and number two, not being used by any other application. Are you getting the point? Not being used by any other application. Now, I'm forgetting the other type of port numbers, but from 1 to 1023, they are called well-known ports. They're called well-known ports. We have well-known ports, we have private ports, and we have another type that I'm forgetting. But well-known ports are the ones that are reserved for well-known protocols. Are we together? You see, like HTTP, we give it port 80. Are we together? So we cannot generate well-known ports. So from 1 to 1023. Then I think either random ports or something. Then we also have private ports. So again, let's just call this random ports. They begin from 1024 to some value which I cannot remember. Then we have private ports. These private ports, again, I can't remember the exact from where they begin from, around 60,000 or something like that to some 64,000 or something. I can't remember, please confirm. But these private ports are used for protocols, proprietary protocols. Are we together? Proprietary protocols. So if an organization is coming up with a proprietary protocol and they want a port number, they can purchase a port number from one of the internet numbering organization. So of course, I mentioned about Afrinic, right? Afrinic. It is Africa Network Information, Network NIC, Network Information, I'm forgetting. But generally we have Afrinic, we have APNIC, we have APNIC I think is for either North America, then another one is for South America. So we have these regional organizations that are used to manage the numbering resources of the internet. So one of those numbering resources that they might control might be, for example, private port numbers. I'm not very sure, but what I'm sure about is that they control public IP addresses, and they also control what we call autonomous system numbers. Okay. So where are we? So those two conditions must be met. The destination port number is the listening port of the application service that has been enabled on the server. For example, HTTP port 80. Are you together? So let's see how this works. Let's see how this works. So you come here, you want to access this server. For example, Huawei.com. So when that happens, your computer will generate a random source port number, for example, 1024. Now, because you're going to a web server, which is HTTP, the destination TCP port number is going to be port 80. On the other hand, this HTTP server has been configured to listen on port 80. Are we together? So that's what we're calling listening. So it will get the request. Okay. And that is why, by the way, you can't be able to open up multiple tabs for the same website. Huh? Because how the computer is able to know is because you're going to have different source port numbers, even though maybe the destination is the source IP address is the same, but you can be able to retrieve several sessions from the same server. The port numbers are going to be different. Okay, TCP connection setup, the three-way handshake. So this is a very important, what do you call it? Concept, the three-way handshake, TCP. Normally it's called a TCP three-way handshake. The TCP three-way handshake is used to set up the TCP connection between two computers. The reason as to why it's called three-way handshake is because you'll have a request for connection, then you'll have an acknowledgement, then after that I'll also acknowledge that, okay, we are now connected. So that's why it's called three-way. Step 1, step 2, step 3, like that. Okay, so it's important that we understand this. So we're just going to go through this step by step. So be a little bit keen. So PC1 wants to initiate a TCP connection with PC2. Are you together? So what happens is that PC1 will, on the TCP header, will generate a random sequence number, for example, A. Are you seeing that A? You remember the sequence field on the TCP header? Yes, unaona sasa inaweka a sequence number, for example, A. Are we together? Then, after that, the acknowledge number during this time is going to be set to 0, because this is not an acknowledgement, right? That's why it is 0. Are we together? Because we've not received anything from PC2. And on the flags field, we are going to set the scene. We are going to set the scene packet. Not packet. The scene flag. I'm sorry. It's called flag. The scene flag is going to be set. Okay. So what happens when PC2 receives this particular packet? PC2 is going to send a reply to PC1. This time, PC2 is also going to generate a random sequence number, for example, B. Then, on the acknowledgement, it's not going to send a 0. It's going to send the sequence number of the packet it received plus 1. Are you seeing that? See, we received sequence number A. So we are going to acknowledge it as A plus 1. Then which flags are we going to set? The seen flag and the acknowledgement flag, meaning that, and by set, by set it means this, by set it means this. Let me just show you. We said we can have 3 flags, seen, arc, and fin, right? Are we together? So on the flags field of the TCP header, you might have 0, 0, 0. You're getting the point? So when we say that seen and arc has been set, it simply means seen is 1, arc is 1, and this one is 0. So when we do the lab, we are going to use Wireshark, which is a packet inspection tool. So when we use Wireshark to capture data, we can be able to go into that packet, into that field, and see these values, just like we're describing them here. Is that clear? So that is what that means. Okay. So lastly, when we receive this packet, PC1 receives this packet with the acknowledgement set to 1, then it's going to reply. This time, the sequence number is going to be, see, my previous sequence number was A. So my second sequence number is going to be A plus 1. And my acknowledgement, on the acknowledgement field, I set B plus 1 because I'm acknowledging that I received what? This segment whose sequence number is B. Are we together? And then on this one, only the acknowledgement field is going to be set. So once we've exchanged these 3 packets, then we have now established a TCP connection. Once we've established the connection, we can now begin exchanging data. So that is what we call the TCP 3-way handshake. The TCP 3-way handshake. Okay, so let's try and make more sense of the sequence number and the acknowledge number, okay? So TCP uses the sequence number and acknowledge number fields to implement reliable and ordered data transmission. Reliable and ordered number transmission. So let's understand how this happens. So when PC1 wants to send data to PC2, the data will be broken down into segments. Into what? Segments. So each byte will be given a specific sequence number. So this sequence number, for example, can be A plus 1. Now, the second byte that is going to be there, for example, so if this is 1, the second byte is going to be 2, then 3, then 4, and so on and so forth. Are you getting the point? I just number them by incrementing by one by one. Now, once the first segment is sent out, I'm just trying. Oh, B plus 1. This one is an acknowledgement. Oh, I think maybe we are. or after the, sorry. Look here. We are now done with the TCP connection. We are done with the TCP connection. So now we want to exchange data. So we just want to look at how the sequence numbers will keep changing, okay? Yeah, so we send this data. We send this data with a sequence number A+1 and an acknowledgement, which was the previous acknowledgement for the connection. Then, of course, with the payload. Now the payload is the data payload, that's the data. Then after that, this guy receives, they have to acknowledge. First of all, they also generate a sequence number, then acknowledge what they have been able to receive. So look here, this is important. So they say, I have received A+1 plus 12. That 12 is this. Are you getting the point? Because this is an acknowledgement, notice the length of the payload. It doesn't have any data, right? Because it's just an acknowledgement. Now, when this guy receives the acknowledgement, the next bit of data it's going to send is going to be A+13. Are you getting the point?
Sorry, teacher.
Yes.
In the acknowledgement, where we've got the sequence, the PC2 acknowledging that it's received sequence, which is sequence is equals to B plus 1. Okay.
Yes.
There's an acknowledgement which is down there, which is acknowledgement. Is it an A plus 12?
A+1 plus 12.
A plus 1 plus 12.
Plus 1 plus 12.
Okay, I didn't see that actually.
Okay. So it's A+1 plus 12 because here you can see here the sequence number is A+1. Because this sequence number is the first byte of each segment. And so the first byte of this segment is the sequence number that has been generated plus 1. So here, the size of this payload is 12 bytes. So when we add plus 12, then we can be able to tell this guy that we've received the data up to this particular point. We've been able to receive this amount of bytes. So send from here going forward. Are you getting the point? And that's why here now, when we are sending this, then we send from A+13. A was the beginning. A was the very beginning. So now we are sending A+13. And we are sending 66 bytes, for example. Then this guy is also going to acknowledge. He's going to acknowledge with the same sequence number, but the acknowledgement, look at it, is now A plus 12 plus 66, which is the size that we've sent here. Are we together? Yeah, so that is how the sequence numbers and acknowledgement numbers are exchanged. I'm sure when you read, you'll be able to understand them better. Okay, so let's also try and understand how TCP achieves flow control. So during the three-way handshake, as we are setting up the connection, one of the fields that we update is the window field. The window field. So we have PC1 and PC2. So You see, this is during the three-way handshake. Step number 1, step number 2, for this data transmission, this is the three-way handshake. Three-way handshake, then data transmission. So during the three-way handshake, as we are sending the connection request, we also send what we can be able to receive. For example, we tell them that we can only receive 3 bytes at a go. Are you getting the point? So this guy will send an acknowledgement, and also tell them that, hey, I can also receive only 3 bytes at a go. Then this guy will send a final acknowledgement with, again, the Windows field set to 3, like that. So after that, we simply now start data transfer, because now we've set up the connection. So we've set up the connection is done. So we now start data transfer. Now, because this guy said they can receive 3 at a go, we can send the first segment with sequence number 101, 102, and 103 at a go. Are you seeing that? Are you seeing that? Then after that, after sending that, depending on how this guy is processing data, and look here, we have the buffer of the receiver. This guy is the receiver. Normally, the receiver has some storage where you're going to store the data before it's picked up by the upper layers. Are you getting the point? So you've received the data. Before it's picked up by the upper layers, until it gets to the application layer where the user will be able to see it, it will be stored on the buffer. It will be stored on the buffer. So the buffer is what determines how much you can process at a go. So generally, if the buffer is a little bit full as you're still processing it, you are still allowed to change the what? To change the window. So like right now, our buffer is still a little bit occupied. So as we acknowledge that we've received up to 103, we now want 104. Are you seeing? We now want 1, send from 104. As we send that, we tell this guy, next time, just send 1 byte at a time. And now the sender, on the next sending, they're going to send just a single what? A single byte, for example, or segment. Is that clear? Yeah. So that is how that works. That is how that works. So that the sender cannot overwhelm the receiver. If you overwhelm the receiver, you send more than the buffer can hold, anything else that comes in is going to be lost, okay?
Hello, teacher.
Yes, please.
I have a question.
Yes, please ask.
You said, where is the 4 coming from? Because you said it is a 3-way sequence.
Sorry, maybe you can ask again. I didn't get you clearly.
I'm asking where the 104 is coming from.
Oh, sorry. Okay. 104 is coming from here, eh? You see, the sender, in this case, the sender is PC1, eh? The sender has sent 101, 102, 103, eh? Are you seeing that? So when the receiver is acknowledging what has been received, it normally indicates what needs to be sent next. So that is where 104 is coming from.
Okay.
Because normally we've been seeing this as A+1, which is the sequence number of the previously received segment plus 1. So that's why it's becoming 104. Okay.
Okay.
Okay. So there's a question here. Why does the window field of the segment sent by PC1 remain unchanged? Why does it remain unchanged? Why do you think it remains unchanged. Because it's the same data. Okay, because it's the same data that is being transferred. Good child. I think it's because that is what it can be able to process. That is what it can be able to process at that particular time. Are you getting the point? Yeah, it's remaining the same because it's telling PC2, if you want to send me data, you can send me 3 segments at a go. Are you getting the point? Yeah, it's indicating its rate. That's my rate. So that's why it's not changing. Unless it becomes busy, then it can change, okay? No, it depends with the buffer size and processing speed of the computer. So 3 is not the limit, okay? Okay, so normally you have to disconnect. We called it connection oriented, right? When you connect, it means at the end you have to disconnect. So the disconnection of TCP is also called TCP shutdown, and it occurs in what we normally term as the TCP four-way handshake. Four-way handshake. So after data transmission is complete, TCP needs to use the four-way handshake mechanism to disconnect the TCP connection and release the system resources. Are you together? So let's see how that is done. So TCP connection is established. That's okay. We've exchanged the data that we want. Now we want to close this connection. How do we do that? Step number 1 is here. We send a connection tear down request with the fin flag being set. Are you together? Are you together? Fritz. So we send that, and this time we set the finished flag. We set it to 1. So when PC2 receives the fin, what does it do? It of course replies with that particular sequence number of the acknowledgement there, and it sets the acknowledgement number to 1. After that, shortly after that, so that's step number 2. Step number 3, it will send a connection tear down request 2 with a fin being set. So we set the fin. Then step number 4, this guy will send an acknowledgement, and the TCP connection will be shut down. So 4-way, 1, 2, 3, 4. We send you, hey, we need to close this. You say, it's okay, I've received your request. Then you send and say, hey, let's close it. And then this one says, it's over. And the connection is done. So that's the 4-way, TCP 4-way handshake. Question? Yes, please.
I'm asking why is it that at the beginning of shutting down the connection, acknowledgement is set.
Or the acknowledgement field might have been set because of this. There was some data exchange process. So there was a packet that was received that had that sequence number 301. So see, we have to acknowledge as we agree to terminate the connection. Okay, network layer, layer number 3. So this is layer what? Layer 3. Layer 3. Which device operates at layer 3? Network device that operates at layer 3?
The router.
Or we also have layer 3 what?
Switch.
Layer 3 switch. Any switch that you especially use at either the aggregation or core layer is most likely going to be a layer 3 switch. So the transport layer is responsible for establishing connections between processes on hosts, and the network layer is responsible for transmitting data from one host to another. So transport layer, connection, establish connection between processes on the host using the port numbers, TCP and UDP port numbers. Network layer, forward data from one host to another host. Are you getting the distinction between the transport layer and the network layer? PDU at the network layer is called a packet. So the network layer is responsible. The network layer is also called the internet layer. It's also called the internet layer. It sends packets from the source to the destination host. Functions of the network layer, number 1, provides logical addressing. So we already said that. Then it routes and forward data packets. So it's just that. So, excuse me. We have IPv4, IPv6, ICMP, IGMP as some of the common network layer protocols. What does IPv4 mean? It means internet version, and we also have
V6.
version. So when you see IPv6, when you see IPv4, then it's that one, okay? Okay, so let's see. So in a network, each device, for example here, we have PC1 and we have PC2. So in a network, each device will have a unique IP address that is used to uniquely identify that particular device. Now, other than end devices, layer 3 devices, the interfaces on layer 3 devices are also assigned unique IP addresses. So we are going to see that as we configure these devices on the lab. So other than the end devices, layer 3 devices, the interfaces of these layer 3 devices are also configured with an IP address. Now, normally an IP address is written in what we call a dotted decimal format. It's normally written like this, for example, 192.168.1.1, like that. So normally at each point, for example, where we've written 192 there, it can range from 0 to 255. Are we together? It simply means that the very first IP address in IPv4 is 0.0.0.0, and the last one is so these are some of the special IP addresses which we are going to look at later. Okay. So when the network layer receives data from the upper layer, packet encapsulation. Let me just see. Oh, this one is just expressing what packet encapsulation is. You remember we said, so you already defined what encapsulation is, right? Yeah. So really, when we receive data from the transport layer, right? Network layer will receive data from what? Transport layer, right? When we receive data from the transport layer, we are going to put it in an envelope. In that envelope, we are going to address it with what? The source IP address and the destination IP address. So that's the very first thing that happens on the network layer. Now, on the receiving end, see here. So the PC encapsulates the IP header. The key information is about the source and destination IP address. Then it forwards it where? It forwards it to the gateway. The gateway really is the router, the interface that is connecting that network. Why are we forwarding it to the gateway? We are forwarding it to the gateway because the PC2 that we want to send to is not within our network segment. Are we together? Otherwise, if we were in the same network segment with PC2, we simply send to it directly. Are we together? Yeah. Okay. Yes?
Sorry for my too many questions. Is it possible for data to be transmitted without encapsulation?
No. It is not possible for data to be transmitted without encapsulation.
Okay. I was just wondering about how does some of the computers get access to information which does not belong to them, the likes of hacking and all that.
Oh, they fake.
Okay.
They fake for example, the source IP address to an authorized IP address, what we call IP spoofing. So that is just but one of the ways.
No.
So really, you can't send data without encapsulation, but you can fake the data among the fields of that particular packet. Are you getting the point? Huh?
Yeah.
It's like me sending to you a very nice romantic letter claiming that it's coming from your boyfriend. I use your boyfriend name and everything on the address. Yeah, but for it to reach, that letter, for it to reach to you, I have to do the addressing, okay? So you have to encapsulate. Okay, so really here, just know that the router will maintain what we call a routing table. Are we together? The routing table will have a list of all the destination networks that it is aware of. All the destination networks that it is aware of. Now, once it receives a packet, it checks, hey, am I aware of this destination? Do I know this destination network? If it knows the destination network, for example, network A, look here, network A, I've found it, I have it in my routing table. Then it's going to look at the other field of the routing table, which is the outbound interface. The outbound interface means if you have a packet that is destined for network A, please send it out through this interface. Normally, every port in a router has a name and a number. Are you together? So for example, G is for gigabit. Gigabit means it can transmit with 1,000 megabits per second or 1 gigabit per second. So that's the name, gigabit. Then the number is 0 stroke 1. So you'll find that if it has another interface, it's G0 stroke 2, and so on and so forth. Is that clear? So we're simply saying you have a packet that is going to network A, send it out through G001. So this is G001. So send it out through G001. When you send it out through that, it's going to, oh, I'm sorry. I'm sorry. Oh, kumbe, I'm pointing to this as router 1, but this is the router 1. Are we together? Yeah. So this packet has been sent here. Then when it comes here, it can either go through this side or this side. But in the routing table, G001 is the one that has been entered in the routing table because it's the best path. So we are going to understand how it determines the best path. So we are not going to send it out through this path. We're going to send it through this path. Are we together? Then after that, it gets here, this guy looks on its routing table, sees that, hey, if I have a packet that is going to network 1, I have to send it there. This guy looks at the routing table, finds, this guy is actually in my locally connected network. So I simply forward it to the destination PC, which is PC2, like that. Are we together? So that is how a packet is forwarded from one network to another network until it reaches the router that is connected to the destination host. Is that clear? Yeah, and therefore that is how IP enables. That is how IP, the network layer, enables the forwarding of data packets. Now, how does a router learn? How does a router learn about this? How does a router learn about these destination networks? It learns through protocols. So we have several routing protocols. I had mentioned I had mentioned RIP in the morning, no longer in use, deprecated, but it's just important to mention it. We have OSPF, we have IS, we have BGP. So in this course, we are going to learn about OSPF. ISIS and BGP, I have extensively covered them in my HCIP video tutorials. They're quite advanced. Just so that you understand, for example, OSPF is used in small networks, relatively small networks, like campus networks and small organization. On the other hand, ISIS is used in ISP networks, mostly ISP networks and any other organization that has many routers. Then you have BGP. BGP is used to interconnect. Sorry about that. BGP is used to interconnect ISPs. Are you together? And these ISPs are normally referred to as autonomous systems. As autonomous, we are going to learn about AS much later. Anyone with a question? Okay, so let's look at the data link layer as we finish up. We're about to finish up this topic. Data link layer is located between network and physical. We already know that. The PDU at the data link layer is called a frame, and Ethernet protocol is the most common data link layer protocol. Why is it common? Because it's used in local area networks. That's why it's common. So data link layer has several functionalities. For example, it provides intra-segment communication for the network layer. It functions include framing, physical, addressing, and error control. Common data link layer protocols include Ethernet, PPoE, and PPP. So we are going to learn about those protocols much later. Ethernet and source MAC address. So Ethernet definition. So when we have a LAN like this one, network A, we have several switches and several PCs like that. Then we call that an Ethernet. Why? Because an Ethernet is a broadcast multiple access protocol that works at the data link layer protocol. So if we have interconnected devices just using the layer 2 device, which is the switch, it forms a single broadcast domain, and that particular network is called, they use the Ethernet standard to communicate. So network interfaces of PC commonly commonly use the Ethernet standard. The network interface cards that we said. Okay, so the Ethernet source MAC address, as we said, every PC has a network interface card. Network interface, this one here. Network interface card. The network interface card has a unique number called the media access control number, which uniquely identifies the NIC, network interface card, on a network. Each NIC requires and has a unique MAC address. MAC addresses are used to locate specific physical devices in an IP network segment. A device that works at the data link layer, such as the Ethernet switch, maintains what we call a what? MAC address table in order to guide the frame forwarding. So this guy here is saying, I have a MAC address when I leave the factory, because it will come. So even your phone has a wireless NIC, wireless network interface card. Your laptop, on the other hand, might have two network interface cards. That is, if it's able to connect wireless and it's also able to connect via a cable. Then it has how many network cards? Two network cards, each with a unique MAC address. Are we together? You can go to CMD, command prompt, the command prompt of your computer. Then you type the command, is it ipconfig /all. You should be able to see the MAC address, all the MAC address of that particular computer you have. Okay. Now, the MAC address normally, here, the MAC address is normally written in 6 groups. 1, 2, 3, 4, 5, 6. 6 groups of 2 hexadecimal digits. 6 groups of 2 hexadecimal digits. Separated most of the time by a hyphen. Separated most of the time by a hyphen. So, for example, we might have a MAC address for a something like that. Hey, R. Hata S hakuna. One, 2, 3, 4, 5, 6. So it looks something like that. Are we together? So normally it's made up of 48 bits. 24 bits is used to identify, the first 24 bits is used to identify the organization. I'm not sure whether we're going to learn about that, but let me just mention it here. So it's made up of 48 bits. 48 bits. First 24 bits identify the organization that made that network interface card. So normally it's called Organizational Unique Identifier, OUI. The other 24 bits is uniquely and incrementally assigned by the organization to that particular NIC. Is that clear? Organizational Unique Identifier, OUI, first 24 bits of the MAC address. The other 24 bits is assigned 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, until they finish all of them, 2 raised to power 24. So anytime we have, for example, a unique identifier for the organization, it means that that is an internet numbering resource which they might need to purchase. for them to use it. Okay, so let's move on. Oh, let's look at another protocol. So far we've looked at which protocol? Which protocols have we looked at? TCP and UDP, right? Yeah, so let's look at another one. It's called ARP. ARP stands for Address Resolution Protocol. The purpose of this protocol is to discover the MAC address associated with a given IP address. We've said for you to communicate in a computer network, you need a physical address and a logical address. Normally, we assign to a device an IP address. But how does it know? How does it know the physical address of the other device? So in order to discover the physical address of the device it wants to communicate to, I already know your number. I'm .1, you are .2, that's my IP address. But how do I know your physical address so that we can be able to communicate at the data link layer? So that's the purpose. That's the purpose of the address resolution protocol. So the address resolution protocol performs the following functions. ARP functions. So number one is, as we have said, to discover MAC of a given IP. Let me just shorten it like that. Then cache. Mapping between MAC and IPs. Number three, detect duplicate IP address. So these are the three functions of ARP. Number two there simply means once we learn that this MAC address belongs to this IP, we store that information for quite some time, so that if we need to communicate with you again, we don't have to do an ARP request again. We don't have to start looking again, okay? So every device will cache, will store temporarily the mapping between a particular IP address and MAC address. Duplicate IP address, sometimes you configure, if you've decided to manually configure IP addresses on computers, sometimes you might configure erroneously the same IP address in more than one device. Are you together? Now, in case you make that mistake, your computer is not going to allow you, because when you configure an IP address, your computer sends out what we call a what? Gratuitous. I think it's supposed to be like that. So it sends out this ARP. This message simply goes out to the network to ask, hey, who has this IP address? Are you getting the point? You configure an IP address on a device, it sends out, who has this IP address? If someone else says, I have it, then Your computer is going to tell you, you can't configure this IP address because it's already being used by another computer. You getting the point? So that is what gratuitous ARP does. I don't know how to pronounce that. So that is how it's able to detect duplicate IP address. Okay, so let's understand. Let's try and understand how this thing works. I'm not sure whether they've explained much on the other side. So host A wants to communicate with host B. Are we together? Initially, host A will just know that the IP address of this guy I want to go to is 192.198.1.2, but it does not know the destination MAC address. Are we together? It doesn't know the hardware address of this guy. So in order to learn the hardware address, it's going to send an ARP request. An ARP request packet is a broadcast packet, meaning everyone on the same network segment or broadcast domain is going to receive that packet. Are we together? Then everyone else is going to ignore it, other than the person whose IP address is indicated on the destination IP address header of the ARP packet. Are you together? So in this case, it's going to be host B. Then this guy is going to reply with an ARP reply packet. Are you together? Yeah. In the ARP reply packet, it's going to indicate its source MAC address. And that is how this guy is going to learn about that particular MAC address. Are you together? Okay, so now let's look at the process one by one. Let's look at the process one by one. So the very first step is here. Step one. Let's call this step one, okay? Step one. Let's read step one. What does host A do? Again, checks cached ARP entries. As I've mentioned earlier, every computer and network device will have an ARP cache table that will store the mapping between LAN MAC addresses and IP addresses. So first of all, before you go ahead to send an ARP request, you have to check in your cache. Do I have it? So that is step one. If I don't have it, then now I send out the ARP request. Are you together? So sending out the request is what we call step two. Step two is here, but we're going to see it in the next slide. If it's not in the cache table, ARP cache table, please don't forget, it's called an ARP cache table. See, this note's quite small. ARP, so some people call this cache. It's supposed to be cache, pronounced as cache, like that. So in your computer, if you open the command prompt, if you type this ARP -A, ARP and then space -A, it's gonna display for you the ARP cache table. The ARP cache table has two columns: the IP address, which is called the internet address, and the physical. Actually, it has three. I'm sorry. It has three: internet address, physical address, and the type. Type simply means how have you learned about this association? Have you learned about it dynamically? Dynamically means you've used ARP, or has it been configured by an administrator? That is called static. So anytime you configure something manually, that is static. If it's done automatically, that's called dynamic. Are we together? So an end device can learn about the association between, or the mapping between a MAC address and an INI by those two ways, either dynamically or statically. So just that. I think I've already explained step 1, right? You check the cache table. So let's go to step 2. So if we don't have it in our cache table, then we send an ARP request. So host 1 will send an ARP request to discover the MAC address of host 2. So the destination MAC address in the ARP request is 0, because the destination MAC address is unknown. Are we together? Yes. Look here. This guy is sending this packet. This packet is an ARP request packet. So it will have a what? It will have an ARP header. Some of the things that are on the ARP header, this thing, they didn't show us the fields. I wish they could have showed us the fields of ARP packet first, but they haven't showed us. But one of the field of the ARP packet is the operation type. Is the operation type. The operation type can either be a request or a reply. Are we together? The other field on the ARP header is the MAC address of the sender. See, that is the source MAC address. Then the source IP address, okay? And then look here, at the destination MAC address, do we know the destination MAC address? See, that is what we want to know. Yes. So we are going to populate it with, what? All zeros. Please take note of that. It's a common question in the exam, okay? On the ARP header, the destination MAC address is gonna be all zeros. Then the destination IP address is going to be IP address of host 2. Is that correct? Okay. So other than the ARP header, the other thing it will have is the Ethernet header, right? The Ethernet 2 header. It's the first time I'm teaching this, but again, in the previous course, we had introduced the Ethernet header before we talk about ARP. But don't worry, just know that we have an Ethernet header, right? The Ethernet header will have the destination MAC address and the source MAC address. So the source MAC address will be the MAC address of PC of host 1, right? Are we together? But the destination address will be all Fs. All Fs means this frame is a broadcast frame. Are we together? All Fs mean this frame is a broadcast frame. Broadcast frame, how is the broadcast frame treated by the switch? You receive the broadcast frame, you send it out to all the connected devices. Are we together? So. But only host 2 will process it. Why? Because they will look at the destination IP address. So. So that is step 2. Anyone with a question before we go to step 3? It's easy stuff, right?
I just wanted to ask a question on
yes.
the ping. You said we can ping ARP-A. On my side, it's failing. I don't know why.
Oh, sorry. I said, I'm not sure whether it can work on your CMD, but the command on ENSP, if you want to check the cache table, of a PC on ENSP, the command is ARP -A. So I'm not sure whether on your CMD you can also use the same. I'm not sure whether the same command is used on Windows. Huh? It's working. On Windows, on command prompt, if you type ARP -A, it brings the cache table, right? Mm-hmm. Okay, so thank you for that. You can just confirm. Oh, we've already gone to step 3. Oh, step 3.
Yeah, it's working. Actually, it's working on this. Yeah, it's now.
Oh, wonderful, wonderful. Okay, so here they're just saying the ARP request message is broadcast data frame. After receiving the ARP request message, the switch will flood it. Please understand this. That action of a switch receiving a broadcast message and sending it out through all other interfaces that are connected to that switch, other than the interface that received that broadcast message, is normally called flooding. It's normally called what? Flooding. Okay, so let's look at the step number 3 actually here. Host 2. Now, what happens is this. Okay, it's step number 4. After this guy receives, host 2 receives the message, it will check whether it is the destination of the message based on the current destination IP address, okay? So it will check, is this destination IP? Does it match mine? If it matches mine, what does it do? It finds the destination message, records the mapping between the sender's MAC address and IP address in its own ARP table. So I will first learn and store the association between the IP address of host 1 and the MAC address of host 1. That information, I'm simply getting it. I'm simply getting it from the ARP request message. And therefore, if on host 2, if you type that ARP space -A, really, it's going to now display, it's going to display that is the IP address of host 1, that is the MAC address, and this is how it learned it. It learned it through ARP. So the value there is going to be dynamic. Are we together? Okay. So let's move on to the next one. So we are on step number 5. So after updating our cache table, and this is a very common question, by the way, on ARP, very common. After updating our cache table, the host 2 will update the cache table. Then it will send a reply. It will send a reply to host 1. So in this step, host 2 has discovered the MAC address of host 1. So the ARP reply, this one is very important. The ARP reply is a what? Unicast data frame. It has to be a unicast data frame. So just find a question, for example, telling you that the ARP reply message is a broadcast message. True or false? Confusing and annoying question at the same time, but you have to deal with it. Okay, so look here on the when you're sending the reply, look at the ARP header. The ARP header, the operation type, what is the value? The value is ARP reply. So now remember, we are now sending this packet, we are now sending it to this guy. So it's a reply. Look at the MAC address, source MAC address, source IP address, receiver MAC address, and receiver IP address. So it's going to be a unicast. Now, lastly, what happens? After receiving the data frame, the switch forwards the frame as a unicast frame. Lastly, here, when host 1 receives the reply, it adds an ARP entry to its own ARP table. Are you together? Yeah, so it will add it there. So you can see if we use the command ARP-A, we can see that the internet address is that, and the physical address is that for host 2, and we learned it dynamically. So step number 7. After receiving the ARP reply message, host 1 checks whether it is the destination of the message based on the carried destination IP address. If so, host 1 records the carried sender's MAC and IP address in its ARP table. So that is the last process that is the last step of ARP. So when you get time, please go through it so that you understand it better. Physical layer, the last layer now. So after data arrives at the physical layer converts the digital signal, that is the zeros and ones, into light or into electricity or into electromagnetic waves, depending on the media that is being used. The PDU is called bit streams at this layer. So it transmits bit streams on the media. It also standardizes features such as the cables, the pins that are used, the voltages, and the interfaces. And common transmission media include twisted pairs. Twisted pairs are simply this cables you're seeing here. Twisted pairs. Next time I'll come with them. Also we have optical fibers, and we have wireless that uses electromagnetic waves. Okay. Transmission media. Today. I'm a little bit slow. Transmission media. We have several. This is what we call the twisted pair. With this transmission media, normally what you need to understand is how it transmits data. Is it using electrical signals or using light or electromagnetic waves? Then it's always also important to know the type of connector that is used to connect that particular media to your device. Then it's always also important to understand the transmission speed. So how fast can it transmit data, and also the maximum transmission distance. Okay, maximum transmission distance. And on,
sorry.
Yes, go on.
Just wanted to know if there's any difference between RJ45 and RJ48.
Okay. I've not even heard of RJ48. What I know of is RJ45 that we commonly use for these computers, and then we also have RJ11 that we use for the IP phones or something. Which one is RJ48?
Actually, nowadays in telecom, we are using RJ48.
Ah, okay, okay. Wonderful. I'll try and have a look at it. So should everyone else. Please make sure you Google and at least learn something about RJ48. Maybe next Saturday you can also tell us, expound more on that. You tell us more about RJ48.
Yeah, sure.
Is that okay, Maurice?
Yeah, that's okay.
Wonderful. So, as I said, those are some of the factors that you're supposed to understand about every transmission media. Transmission distance and also the different types. For example, for twisted pair cables, we have Cat 5, we have Cat 6. So you need to understand those different types. The speed, so this is a reading assignment I'm giving you. The transmission speed and maximum distance that they can cover. So please make sure you read about that over the week. This is the most common. This is the most common on local area networks, twisted pairs, and they use the RJ45 connector. During the boot camp at the end of the training, I hope we will at least learn how to crimp, how to connect this cable with the connector. It's called crimping. So how to do that? It's one of the things that we'll plan for the boot camp at the end of the training. Then we also have fiber. Fiber uses light to transmit. Data transmission through optical fibers is also possible. And normally we have an optical module. Oh, something I didn't say about the twisted pair. We have what you call a shielded twisted pair and unshielded twisted pair. STP. It's important that I need twisted pair, STP, and we also have unshielded. Twisted pairs, UTP. So that's the other thing that you have to consider whenever you're going to buy these cables. Shielded simply means it has an aluminum foil. It normally has a shield, which is an aluminum foil that helps to reduce electromagnetic interference. So that is what is called shielded twisted pair. But otherwise, unshielded twisted pairs just have the wires that are intertwined together, but they don't have any other protection other than the outer coats. With fiber, normally there are two main functional components for the fiber. That is the fiber itself, which is the optical transmission media made up of glass most of the time, that is used to transmit data using light. Then the other thing you need to know about is the optical module. Now, the optical module is used to convert the electrical signals into optical signals. Are we together? And vice versa. So that is the optical module. Optical module used to convert electrical signals to light signals. We also have serial cables. Serial cables are quite important. One of the serial cable is the console cable that is used for the initial configuration of switches and routers. Then of course we have wireless. we have wireless transmission. Okay, so I think just a summary of the data communication process as we wind up. So let's begin from data encapsulation on the sender side. So you type, you want to go to Huawei.com. So at the application there, it's just data. And then, of course, everything that happens on the session layer and presentation layer will happen at the application layer. So encryption, data formatting, session formation, and so on and so forth. Then at the transport layer, we're going to add a what? A TCP header. Are you together? Then on the network layer, we are going to add an IP header. Okay. At the data link layer, we add a what? An Ethernet header, and we also add a trailer. That trailer is what we call a frame check sequence. Call it what? Frame check sequence. So the frame check sequence is used for security, just to confirm that this frame has not been tampered with during transmission. So almost like the checksum. So frame check sequence. Then lastly, at the physical layer, the electrical signals are going to be converted to a form that can be transmitted using the particular transmission media. So that is what we call data encapsulation. When we are sending, data is encapsulated. Data transmission on the intermediate network. It's important that you also understand this. So when we send this data to the switch, the switch is going to open it up to the data link layer. Are we together? Because the switch simply needs to know the destination MAC address. Is that clear? Then the switch is going to send it to the router. The router, on the other hand, forwards using IP address. So it's going to open up that particular packet up to the network layer so that it can be able to see the destination IP address. Switch will look at destination MAC address. Router will look at destination IP address. Then send it. When it gets to the owner will open it up to the application layer and see everything that is in the data payload. Are we together? Yeah. So that is what happens. Now, generally, maybe something else that I need to mention is this. Remember, there is no way this guy can know the MAC address of this guy. Are we together? Reason being, they are not on the same network. So you see, they are separated by a router. Every interface of a router creates a different network segment. Are you together? So they are on different network segments. So what happens is, if I want to send to this guy, the MAC address that I have to get in order to send to that guy is the MAC address of the gateway, the MAC address of that interface. Are you together? Yeah. So I have to get the MAC address of this guy. Then once I get the MAC address of this guy, I'll say that destination MAC address is this one. When this guy gets it, looks at the IP, destination IP address, it's gonna change the MAC address now, the destination MAC address to the MAC address of this particular interface. Are you getting the point? Yeah. So that is how it works. I hope it makes sense. Oh, decapsulation is the opposite of. Decapsulation happens where?
At the receiving end.
On the receiver, exactly. So on the receiver, data will move from the transmission media into the physical layer, from the physical layer to the data link layer. At the data link layer, it's gonna look at the destination MAC address. Is this my destination MAC address? Does it match? If yes, I will remove the header here. I will remove the header, and I will also remove the trailer, the frame check sequence. You getting the point? Then I'll forward that particular packet up to the network layer. The network layer again will confirm, hey, is this does the destination IP address match my own? If yes, then I'll remove the IP header and forward this packet to the transport layer. Are we together? Transport layer will check, is the port number and the sequence numbers and everything, is it mine? Is this connection legit? Okay, then I'll remove the TCP header and forward only the what? The data to the application layer. Then once the data is on the application layer, the user can be able to view it, for example, using a browser if you are accessing a web server. So you can be able to see it. Is that clear? You still remember this? So next time when I'm talking of a frame, you know which layer I'm referring to. Okay. Finally. So that's the summary. Please don't allow me not to go through it here. And allow me to ask you to discuss these two questions just now. Is that okay? Yeah. Normally we have the answers below the notes, which you can also refer to in case you're not able to answer any question. I'm saying this because of those ones who are online and they don't have anyone else to discuss with. But try and brainstorm about these two questions. Then we can communicate after that. Thank you very much for your patience and participation.